Okay, so this is your topic one, building science and services one, lighting in building. So as previously mentioned, when we are talking about lighting in a building, we know that in a building, there's actually a mixture of natural light and artificial light in a building. So based on this picture, what we can have from our natural light is from our sun. So during the day, we actually have sunlight. So how this sunlight can be accessible into our building is through all these opening in our building. So we can have window, we can have glass door. This can all allow sunlight to come into our building. So this is all free, and that's why we should try to make use of it in a building. So if we use or we open artificial lighting, which can be from different form. It actually consume electricity and will be charged for it. So you have to study a bit more on what is uh, light, and then how we can measure it, how we can choose the most correct form of light, and then how we can calculate the amount of lighting required in a room. We will be discussing it in this topic. So in these slides, you have all the basic information that you're required to be that we will go through, and then after that, I will show you guys the other supporting document in which we use in Malaysia, where we can use where it showcase that what you have learned in this topic is actually relevant to what you can actually apply it in future when you're working. Okay, so there's 8 subtopic in this topic one. The first is lighting. The second is the measurement of lighting. And then the third, you have your lamps, different type of available lighting. And then you have your luminaries, artificial lighting design, and then your natural light source, daylight factor, and combined lighting. So all these subtopic is actually available, is what is covered in your course syllabus, which is here. Okay, so here there's actually a glare, which is not mentioned here. So, but in your lecture slides, there's the subtopic there's a content for it. Okay, so for this subject, we have your core reading list, which is how this material come about. So how this lecture slides is created, it actually came from these 2 books, which is the Hall F. Grano and Mark Mellon. So for other subject, you can always refer to the course syllabus, and at the end of the page here, you can see that this is the reference. So for this subject, the main reference is here, which can be located. So same goes for your lab. They also mention what sort of lab that can be done for this subject. Okay, coming back. Okay, so for this topic, you should be able to achieve a course learning outcome of 1 and 4 after you're done with this topic, hopefully. And then you'll be tested based on this 1 and 4 for your assessment. So for your assessment, for the coursework, is quite easy in a sense that there will not be any test. You just need to submit the assignment. And then for the final, I'll be giving you guys a sample or a trial for you to have a look, and you can do it later on. So that final, I will let you guys know. I will brief you guys more on it at a later date . Okay, so a quick video which I found that is quite relevant and interesting. Let's have a look at it. Okay, so we learned a bit of what lighting is all about lah from that video. So for a light, it's just actually a photon. So it's just a form of energy, and there's no mass in it, and it's just nature lah. What how light is just a form of nature that's all around us that has been around for a very very long time. So as mentioned, there's actually a very wide range of light or this electromagnetic spectrum available, and we have actually evolved to just be able to detect or see just a very tiny spectrum of it. Okay, so because light is an energy, so they actually require no medium to travel, and all these electromagnetic wave they actually have a very very high velocity, and they travel at the same velocity. But what's different between each of them is they actually have a different uh, frequency. So their wavelength might be they'll have a different wavelength as you have seen through the video here. So that's why although they travel at the same speed, but based on their wavelength, they have different characteristic. So next off, we have visible radiation and invisible radiation. So this visible radiation is what is categorized as what we can see. So white light is a visible radiation. We can see it. We have evolved to be able to identify this white light from using our eye, and when we are actually using a prism, we can actually see the different wavelength from a white light into these seven rainbow colors. Okay, so there's actually other non-visible radiance available, but here let's just talk about two of them. Yes. So we have the infrared IR. So this is actually greater wavelength that's greater than the red light, and there's many usage towards it. We can actually use it to detect patterns of heat emission, meaning instead of physically measuring the temperature of object in close contact, we can actually measure it from a distance away, or we can use it to see in the dark, which is what some of the animals use because they have evolved to be able to see infrared. So if we have an infrared device, we are actually able to see in the dark, but it will be in a black and white images. And then finally, we can use it for communication link. So why we cannot see infrared is just a step of evolution in our process. So some animal they have developed the means to see it, and we have not. So this is just a step of evolution in our life. Okay, so next we have our UV. So the sun actually emits UV light to Earth, and we actually need it for our body, but it can be damaging to us if we are exposed to it. Okay, so this is just a property of what light is about. So light is something that is all around us, something that seems very simple, but we still don't know about we don't know 100% about what all this is all about. Okay, so when it comes to perspective of a building, we want to be able to we want to be able to measure what is the required amount of lighting we need for a building. So for different places or different requirement, you want to know how much or how bright a light that we can install in a room. So that's why we have all these theories and measurement that comes about. So first off, you want to understand a bit of the different properties of a lighting. So the first one we have is the luminous intensity, meaning how bright a light is compared to the other light source. So the unit for this is a candela, which is represented by CD. So luminous intensity is used to compare different light source and measure their strength. So this is the first property. So for the second property, you have your luminous flux. So luminous flux is the rate of flow of light energy, which is lumen. So there is a formula here. So you have I, which is how intense light source is, equals to flux divided by this omega. This is W lah in Latin, and we pronounce it as omega. So this omega is actually a solid angle containing the flux. We call this as a stadium. Okay, so bear with me lah for a while. So we know that I is the luminous intensity. So different object, when we are designing lighting appliances, they will have different light intensity. And then when it comes to the flow of how this lighting travels, meaning as they travel further, you notice that the light gets less brighter. So light is a form of energy. As they travel, if they are not powered, they will actually lose their power along the way. So this formula has been come out lah to uh, to theorize that. Okay, so next we actually have, if you look at it here, so when we consider a point source of one candela emitting flux in all direction, the total solid angle around a point is 4 pi stadium. So a bit more information on what a stadium is. So a stadium is actually this cone shape. So what makes a total solid angle around a point? So this total solid angle around a point is actually the stadium. So if you take a sphere, we find out what is the surface area of it, and we divide it by an area giving one stadium, which is equivalent to r square. We will work out that a total solid angle around a point is 4 pi. So basically what I just mentioned to you is what this information on top is trying to let you know. So one stadium is the shape of this cone, uh, so which is represented by this formula. So this is a formula lah. This is already dead. So this is how one stadium comes about, which is omega, and it will always be represented by 4 pi. So in a sense, this is all explanation. You can assume one stadium is equals to 4 pi. So that's where this uh, formula comes about. When we substitute omega with 4 pi, you get this F equals to I multiplied by 4 pi. Okay, then finally, we have illuminance. So when you have a point, when you have a diagram such as like this in real life, you are actually able to measure how intense the power source, the light source is. So we can represent it, we can represent this lighting source with I, which is the candela. And then for the flow of light energy, which is flux or lumen, from a point A to point B, this can be calculated using the formula here. And then finally, the most important thing when we are doing lighting calculation is knowing the illumination on the surface, which is the lux. So I will go through a bit on the calculation, and then after that I will show you guys later on why this lux is important lah when we go towards the industry and we go towards lighting calculation. So in Malaysia we are not really uh, big enough lah, meaning we are not diverse enough to actually have a lighting consultant. So if you go towards other country, maybe the US, where everything is where it's big enough and there's a big enough opportunity to be a specialization in such a tiny field as a lighting consultant, then all this will actually really comes into play lah, because there's actually a need to calculate the right required amount of uh, lighting design. So why I said that this is important is because when we look towards the sustainability point of view, you imagine we have a building. So to build a building, it actually requires 2 to 3 years, which if you think about it is quite long. But when it comes to operating a building, think about it. Operating a building, how long has the building that you're occupying has been there? How long have you occupied a building? If you think about it, actually a building, you can occupy a building for up to 100 years. So think about it, about all the services in the building. Have they been optimized? Meaning, did you put just the right amount of lighting for the required area? Did you put too much or did you put too less? So if you put too much lighting in a particular area, you are actually wasting energy. So that's the bad point in the sustainability aspect lah. So you're actually wasting your electric energy for, let's say, your building will still be operating for 70 more years. So you'll be wasting electricity for 100 years or more as long as the building is being operated. But if the lighting that you installed is not enough, then it's not, you'll find that this area will not be really fit for purpose lah, to be used. So that's why the study of this calculation is very important when it comes into uh, building. So definitely, if you experience it yourself, you look around, you notice that the brightness in your house is not as will not be as bright as what you see in the shopping mall. So you'll notice that when you go to a shopping mall, although maybe some of you guys haven't been to a shopping mall for a very long time, you'll notice that shopping mall, they are quite bright as compared to your standard housing. And then if you go towards those jewelry shop, then you'll notice that their lighting there is even brighter as compared to other places. Or if you go to a display unit, maybe you go to look at a phone shop, then you notice that they actually installed very, very bright light for you to have a look at their product. So this is all marketing strategy lah. Okay, so coming back to this, so based on the formula that you have been given, you'll be able to work out the calculation for lux or the required intensity for an area. So usually when it comes to lighting calculation, what we are more interested in is the illuminance here. So how much illuminance is hitting on the surface. So if you do not have enough brightness on this surface, how our eye works is that the light will hit on this surface and it will actually reflect into our eye, our human eye. So how well or how detailed we can see the surface is based on how much light is reflected off this surface into our eye. But since we are not going so deep into it, what what we are required to find out is the required level of lux. So we are taking away the aspect of calculating another step of the reflection of this lux from the surface to what we are able to see. So what you're learning in this topic 1 will just be how bright is this surface area will be required. Okay, so for the illuminance, you are given E equals to F over area. So area is how big of a surface the total flux that's traveling needs to illuminate. So if you have a bigger area, then your flux will be lesser, the flow of light. Okay, so example 1. So in this example, you're given a light source which have an intensity of 100 candela. And as mentioned here, only 1/4 of this total flux falls at a right angle onto the surface. And this surface is given by this area. So you're actually required to calculate what is the total flux given out by this light source and what is the illuminance produced on the surface. So right off the bat from this example, you can extract that the I is equals to 100 candela and the strontium, which is omega, represented by this W, is equals to 4 pi. So this you don't have to calculate. You just assume your strontium as 4 pi, and then you are required to find out what is your flux from this source. So remember, back at this picture, the flux is the flow of light. So from this source, from this light source I, you'll be able to work out what is your luminous flux, the flow of light energy that flows out from your light source. And then from this flux, the amount of flux emitted, the lumen, you'll be able to work out what is the lux required or lux that has been achieved on the surface based on this luminous intensity. Okay, so the first formula that you require is this I equals to F over omega. So if you substitute all the value that you know with 100 candela here and 4 pi, you work out that your flow of energy is equals to 1256 lumen. So that is your total flux. So next off, you need to find what is the illuminance produced on the surface. So pay attention that because this question mentioned that only 1/4. So if this question didn't mention only 1/4, it just mentioned that it just mentioned to you to find what is the illuminance produced on the surface, then you don't have to multiply it by 0.25. So this example, because they mentioned 1/4 of the total flux emitted falls at right angle onto a surface, then you have to take into account this 1/4. So that's why you have to multiply by 0.25. You get a value. This is the actual flux that falls at the right angle to the surface. And then from there, you apply the formula E equals to F over A. So the A is the area that's given to you, 3 meter multiplied by 0.7. And you get that the illuminance on that surface is actually 150 lux. So this is how the formula that you're given can be used to calculate how much lux has been emitted onto the surface. So for this theory that we have gone through, the important thing is this and this. Knowing that the omega is equals to 4 stradivarium. So you can replace the omega with 4 pi. Okay, so this is the most basic lah. If you are just given just single distance, you are not given a distance on how far a light is measured from. So when it comes to distance, we know that we are given the inverse square law of illuminance. So based on the inverse square law of illuminance, as the light travels further and further away to light up a surface, the illuminance actually decreases in proportionate to the distance. So at just at a specified distance, we have illuminance at the surface. But if we multiply that distance, the amount of illuminance reaching that particular surface is just a quarter of it. And if you were to increase further the distance, then it will be reduced by another quarter. So this is what it means by inverse square of illuminance, which is represented by E equals to I over D squared. So the illuminance on a surface is actually equals to how intense, what's the intensity of the point source divided by the distance. So the further away, the less illuminance that will reach the surface. Okay, so example 2 showcase how this formula can be used. For an example, so we have a lamp with a luminous intensity of 1200 candela, and it can act and is acting as a point source. So we are actually finding out, we are given the option to calculate out what is the illuminance produced on the surface at 2 meter and 6 meter. So using the formula E equals to I over D square, where I is represented by a fixed value given from your example, which is 1002, divided by the distance. So the surface at 2 meter and the surface at 6 meter, they will have different amount of brightness that's able to reach the surface. So when we calculate it out, we found that at 2 meter, there's actually 300 amount of lux reaching the surface, and then at 6 meter, only 33.33 lux reaching the meter. So this is all just theoretically, just a theoretical calculation lah. So to work out the actual one, then we will actually have to go through our first lab experiment to find out that is the theory, the formula given out, does it tally with what our theory that we can work out. So this is important like in terms of for a science subject, you want to be able to verify the formula given to us. So we are not here to derive or create formula because this has been done extensively by other scientists to give it to us, so we don't have to go and figure it out how this formula come about. What we are learning here at the university level is about verifying this formula, and then if you want to go further and learn more about it, that will be up to you to learn more about it lah, how this formula come about. But what you learn for this subject is you learn about the theory about it. You learn that the formula is given to you like this, and then we can do a lab practical to verify that this theory or this formula is what is workable lah. You'll be able to apply this formula to real life situation. Okay, so secondly, we have your cosine law of illuminance, or we call it Lambert cosine rule. So this cosine law basically just mention so this cosine law of illuminance is basically the same as this inverse square law of illuminance, if you notice it. So you have your E equals to I over D square, and here you have your E equals to I over D square cos theta. So this is basically the same as the inverse square law of illuminance, but instead of the light source striking the surface at a right angle, now the point source is striking the surface at a inclined angle. So that's why this cosine law of illuminance come about. So we have to add a cos theta based on how many degree of inclination the angle for the light is to hit the surface of the illuminance. Okay, so based on here, we will be able to find out at different point how bright it is. So we will be able to make use of this formula to find out the minimum and maximum illuminance for a surface area. So this is how the formula comes about. Okay, so I will finish this example and there about it lah for our this lecture session. So example 3, we have your cosine law of illuminance, how we make use of it. So a lamp with the intensity of 1005 candela, so it is fixed 2 meters above the center of a circular table. So it's 2 meters above a table, and this table has a radius of 1.5 meter. So you are required to calculate what is the illuminance provided at the edge of the table, and you have to ignore the reflectors illuminance. So to work out what is your illuminance at the edge of the table, you know that your I is equals to 1005 candela. So to work out the distance at the edge of the table, you will need to use the triangle law. So you know that you know the height between the fixed point and the center of the circular table is 2 meter, and you know that the radius is 1.5. So imagine this is your example. So here you know that this is 2 meter, point source towards the center of the table. And imagining this is the edge, so the question mentioned that the r is the radius of this circular table is 1.5. So 1.5 is from here to here. So when you read your question, please pay attention towards it. So the question might mention diameter or radius. If you mention radius, then you can just take the value and put it into the triangle law. But if it mentions diameter, which is the whole length of a circle, then you have to divide it by 2 to get your radius. Okay, so using the triangle law, you know that here, square, A square here and B square here, you get a C square here. So this is how you get your D. So if you work it out, you'll get that your D is actually 2.5. Okay, so coming back to here, you know that your E equals to I over D square multiplied by cos theta. So based on this triangle law, you're actually able to get what is your D, which you can put it here, 2.5. You know what is your I, which is 1005 candela, but you don't know what is your cos theta. So the question did not give you a angle at, at which the light falls at the edge of the table. So based on that, you actually do not need to, as mentioned here, you do not need to know the angle in degree. So what you can do here is you use the trigonometry law, which is you have the cos theta equals to adjacent over the hypotenuse. So this is the sides of this triangle. So you have your adjacent, which is 2 meter. This adjacent is the height of your light source to your table, which is 2 meter. And then your hypotenuse is your D, which you have worked it out. So you divide 2 over 2.5, you get 0.8. So this 0.8 is actually equals to cos theta. Okay, so I think I need to change a bit. Okay, so I put this. Not to be confused. Is it correct? I think I shouldn't change. Put this. Okay, so hopefully this is clear to you guys. Think like this is alright. So this cos theta equals to adjacent over hypotenuse. This is a trigonometry formula function. So you can look it up online or find it out. You'll be able to find out this equation on the trigonometry table. So as mentioned here, you don't have to know it. You can apply this formula and you'll be able to get a value, and you can remove away this cos theta. Okay, so with this 0.8, you can put it into this formula and you can solve this equation, and you'll be able to get that the illuminance at the table edge is just 192 lux. So as you notice here, the cos theta here actually give a multiplication value of less than 1. So this actually showcases that at the edge of the table, you're actually getting a lesser value of lux on the surface. So with this formula and this formula, the inverse square law of illuminance and the cosine law of illuminance, when you combine both of these together, you'll actually be able to find the maximum and minimum value of illuminance in the surface. So this inverse square law of illuminance give a point source of light onto a surface on how bright it is. And then for the cosine law of illuminance, it mentions light striking the surface at an inclined angle. So both formula is very similar, where only one of the differences is the cos theta added. Okay, so this will be enough for your assignment for your tutorial 1. So I will stop here and then we can continue the rest next week.